We're going to use a transistor to build a different device than just an output of a power supply. And what we're going to build is we're going to build an amplifier. As indicated here, an amplifier has an input, which I indicate is a fairly small amplitude sine wave, and then it produces an output, which is a replica of the sine wave. It's just a greater amplitude as indicated here. This happens to be an example of a amplifier with a gain of 4. What would be the utility of this if this is a very quiet sound that you're hearing through your headphones? This would be a much louder sound you're hearing through your headphones. The way we're going to start is we're going to start from using a transistor, and we're going to try to use what we've done before in order to build one of these things. And so we start with a common emitter configuration. It's common emitter because we're pulling the output off the emitter, and the emitter is connected to ground through a resistor. Well, if we put an input into the base, okay, we apply this potential to the base. First thing we know is the potential has to be above ground, because we have to keep the base 7/10 of a volt above the emitter. So it has to be up high, is indicated here. If we look at the emitter it has the same potential as the base, but with the exception of a 7/10 of a volt drop, which is the base to the emitter. It's that diode drop from the base to the emitter. So the output would look something as this. Well, what's the problem with that output? The output is basically shifted, but it's a one-to-one amplifier, and we pretty much should convince ourselves we can't build a useful amplifier using a common emitter. Okay, so let's go through and let's see how we're going to do this, but in order to do it, we're going to have to look at how to bias a transistor. So how do we get a transistor where the collector potential is above the base potential, and which is in turn above the emitter potential? And the way we do it is we add this little resistor network out here. Purpose of the resistor network is to do no more than establish a base potential, VB, such that all of this stuff works for us. Okay, so let's look at a very simple example. Simple example was, suppose that we want the base to be 1/2 of this potential, and this is generally called VCC. Okay, so if we want the base to be 1/2 of VCC, so VB is equal to VCC over 2 to get us biased, okay, then all we have to do is set R1 equal to R2, and then we'll find out that that works. If we did that, then we would have a situation where this potential would be VCC over 2, the emitter would be 7/10 of a volt less, and the collector would be up here at VCC. So all this would be good. We'd bias our transistor. So it's not that easy to do it. We're going to find how to do it in a little bit more detail. Okay, so let's look at of biasing a transistor here. And so we suppose that we have a situation where we have VCC is 12 volts right over here. We have we just arbitrarily set the emitter resistor to about 500 ohms, and then we want to find a pair of resistors here so that the output potential, VE, is equal to 4 volts. So we want 4 volts here. In order to get 4 volts here, we need 4.7 volts on the base. So what we do is, let's ignore the base current, which is good. R1 and R2 form a voltage divider, so all we want is the voltage divider to ratio to about 1/3. We would go through and simplify this, okay, and we'd find that the ratio looks something, we want R1 and R2 to look something like this. If we arbitrarily set R1 equal to 1K ohm, 1,000 ohms, we would find that R2 is about 1,500 ohms in this. Now, if we said R2 was 2,000 ohms, then we'd find R1 would be 3,000 ohms. So it's the ratio we're interested, not the values. Okay, so was it okay in our previous example to ignore the base current? I'm going to do this really quickly. The base current is just equal to the base potential, okay, I should do it from here. Base potential, which is 4.7 volts in this case, times beta plus 1 times the base resistor value. In this case, the base resistor is about a half a kilo ohm or 500 ohms. That means that in beta is about 50, so we're dividing the base current by about 24 k ohm. Okay, what's the current that's flowing through R2? Well, it's the same thing. It has the same um, potential across it, but it has, in this case, it's only 1 k ohm because this is 1 k ohm value. And so it's very clear to see that the amount of current going through R2 is about 24 times that's going through the base. So if we ignore the base current, we only end up with a 4% error. Now, if you want to not ignore the base current, all it does is add a little bit more algebra to your calculation. But in many cases, we can ignore the base current. It makes it easier, and it doesn't really change the design. Okay, so let's return. Now we know what these R1 and R2 things are about. Now we're going to actually build an amplifier, and we do so by adding this resistor, which is a collector resistor, and we do so by moving the output from the emitter up to the collector, so the output comes out of the collector. Okay, so let's see if we can figure out how this thing would work. So I'm going to start assuming that I properly biased it. I'm going to bias this so that this this point right here, the base voltage, is equal to 4.7 volts plus some little delta. And so this is going to be representing my signal. Delta can be positive or negative. Okay, so if I do that, okay, then what I notice over here is that the collector will be 7/10 of a volt less. So it's 4 volts plus delta. Okay, we don't subtract delta. We're subtracting 7/10 of volts from the base voltage, not from 4.7 and delta individually. So that's why we just have one case. So if that's the case, we can find the change in the collector current, this little delta IE. And delta IE is equal to delta over RE. So that's the change in the emitter current. If we know the emitter current, we can back up and we can find the collector current. And the collector current is the emitter current, which we've already computed, the change in the emitter current, okay, multiplied by this beta over beta plus 1. Many times beta plus 1 is approximately equal to 1. So we just simply ignore it. So, but we'll carry it through. So now that's the change in the collector current. Okay, now if I know the change in the collector current, which is this from the previous slide, okay, then I know what the change in the collector potential is, okay, because that just causes a change of this across RC, okay. And so why do I have a negative sign here? Because, well, this is the current, okay, that's changed. This is the change in the current, the thing I'm boxing. This is the resistance of RC. So this is just application of Ohm's law. So that's a change in the potential across RC, and it's negative because if I increase the current through RC, I actually lower the potential on this output because there's a greater potential between the collector and the this VCC. So what happens here is I look at this and I say, okay, that's a change in the potential right here. So this is the change in the potential, okay, at the collector or the output. In order to get the gain is the change in the output over the change in the input. So I just divide this by delta. The deltas cancel out, and this is the gain. So the gain is negative 1, approximately 1, times the ratio of RC to RE. And so this is generally what we go express the gain. So the gain of this amplifier, indeed we have an amplifier, is just simply determined by the values of the emitter resistor and the collector resistor, which is surprisingly simple. Okay, so let's go through and see if we can do this. Okay, if we insert a 2.3 k ohm resistor for RC, okay, then we would find that 2.3 k ohm, okay, divided by the emitter resistor, multiplied by beta over beta plus 1 is approximately equal to 5. And by the way, it's not 5, it's, remember, we always get a negative sign here. This always inverts that signal as we run through. Okay, so that's how we compute the gain. We compute the gain of our amplifier by looking at these two values. Now, before we get all excited that we actually did this, let's make sure this thing works. Okay, so the main problem I have is I want to make sure that everything's biased right. So because of R1 and R2, we know that the base voltage has to be 4.7 volts. Okay, because the fact that this is the base emitter junction, we know that the emitter voltage wants to be about 4 volts, okay, without a delta. We're not adding a signal to it. Okay, and since this is about 500 ohms, we know that the current, the emitter current, is about 8.5 milliamps. So we know that we have about 8.5 milliamps going through there. Okay, so that's what we know so far. So let's go through it and continue our discussion. So we know that if there's 8.5 milliamps going down here, okay, we know there's about 8.5 milliamps going down there, okay? So what we do is we multiply 8.5 milliamps, and by the way, this should have been 23. We multiply 8.5 milliamps by this collector resistor, and we find there's about 20 volts across the collector resistor. Hold it. We got a problem because we know that the potential difference between this point and this point has to be 12 volts. But now we have that this is the current 8 milliamps going through the collector resistor would give us 20 volts. 8 milliamps going through the emitter resistor gives us 4 volts. That's greater than 12 volts. So this 4 plus 20 is greater than 12, which means this is impossible. So we made a mistake when we did the calculation. As a matter of fact, the maximum current that can flow through the collector or the emitter. Okay, let me pick this up again. Okay, I return. I flipped a slide too quickly. The maximum amount of current that can flow through the collector or the emitter can be computed by looking at the maximum potential between the collector and ground, which is 12 volts. Divide it by the sum of the collector resistor and the emitter resistor. And so it's only about 4.3 milliamps. So 4.3 milliamps is the maximum amount we can carry through the emitter. So what do we do when we're actually dealing with this then? So obviously we're going to have to change our design. And so we can change our design in a bunch of ways. Probably most people would look at this and say, I'm going to change my design by making the collector resistor smaller. So if I put it 500 ohms, okay, and also if I make the emitter resistor 500 ohms or 100 ohms, so I get a ratio of 5, okay, we would think that it would work, but all that does is increase the current through this transistor by a factor of 5, and as such, it doesn't change the potential drops. So this won't work. So we can't be more clever. Okay, let's figure out how to get out of this pickle by looking at the maximum amount of potential we want to drop across the collector resistor. Let's say, and I somewhat arbitrarily say, let's say that we want 5 volts to normally drop across the collector resistor. So let's work backwards. Okay, if we want 5 volts to drop across this 2.4 or 2.3 k ohm resistor, how much current do we need? We need about 2 milliamps here. So we want about 2 milliamps to go through that resistor. Now, if we have 2 milliamps going through that resistor, then within within that factor of beta over beta plus 1, we have about 2 milliamps going through this resistor. Okay, and so what we have is we get about a 1 volt drop here. So this is 1 volt. So we can get this to work, okay, looking at the potential drops, as long as we keep the emitter down to about 1 volt. So how do we get the emitter down to 1 volt? That means we need the base uh, potential to be about 1.7 volts. Okay, and that means we have to resize R1 and R2 because we're going to divide 12 volts now down to 1.7 rather than that 4.7 we did before. So if we arbitrarily keep R2 at 1 k ohm and we increase R2 now to 6 k ohms, so we have 1 k ohm here and we have 6 k ohms here, we would get this base potential down to about 1.7 volts. So that looks like we have a much better chance of making it work. Let's go through and take a look at the numbers and make sure they work. So we're going to check it, and we check it by doing the following. We make sure we're going to ignore IB again, which is okay. We look at this as the potential drop. This is the ratio of the R1 and R2. We're applying 12 volts to it. We get 1.7 volts here. So we check. The emitter is down here now at 1 volt. We check. So the emitter current is 1 volt divided by 470 ohms, which is the resistor, the emitter resistance. That's 2 milliamps. Check. Okay. And so now we go through, and in this case, I'm not ignoring beta or the 1 plus beta thing. So we do it formally, and that means we need about 2.06 milliamps through the collector. Okay. If we have 2.6 milliamps to the collector, then we find that the potential of the collector, which is right here, is going to be 12 volts minus the potential drop across the collector resistor, which is 12 volts minus this, and then that's about 7 volts. So this guy is sitting at 7 volts. And guess what? We have 7 volts. We have the base is 1.7. The emitter is 1. It looks like we properly biased. And because of the ratio of 470 ohms to 2.4K is about 5.1, we have the right gain. So guess what? We have a working circuit. Okay, now the one question we've come up with before we're looking at this thing, we have some input that we called this thing delta. It was some small perturbation on the base current, on the base potential across here. Okay, so actually, how do we get a little value or a little signal into this thing? And the way we do it is the following. The first thing we have to assume that we're not interested in the average value. So this is an electrocardiogram. The ground appears like this. The average value here looks like this. The average value of this looks like this. What we're saying, these are all equal. So we're not interested in the DC on this thing. So this would be a case where we have some little circuit in here. Now, in order to get it here to make a delta on the bias base potential, we need to get a capacitor here. What this capacitor does is this capacitor basically has a potential across it. It reaches a potential, which is the difference between this bias and the DC component down here on the input. So now this input looks like this. And notice what happens. The input is no longer at 0, but the input now is sitting up here. It's oscillating around 1 volt. Now we do the same thing in the output. Notice that the output here is oscillating around, looks like about 7 volts, okay, as we talked about before. Okay, we put another capacitor here. That capacitor charges to the average difference between them, and so the output would look like it's going around 0. So it looks like we got that by doing these these capacitors. So with that, you should have enough background to design a simple amplifier, and with the AC coupling, we should be able to put a signal into it and see if it actually works. That finishes this video.